This video is on process control signals. After completing this module, you should be able to define and explain the flow of process control signals, identify the process and signal sides of the process control signal path, define and explain the following process control terms: range, span, zero, offset, industry standard signal, dead time, dead band, and dead zone. Let's look at instrumentation in its simplest terms. What, as electricians, are we trying to do? We are trying to convert something like the level of water in a tank into a usable electrical signal. That's pretty much it. That's instrumentation in a nutshell. This may be oversimplifying it, but essentially, as electricians, well, we'd rather let electricity do the work for us instead of climbing to the top of a tank with a dipstick every 10 minutes just to see how much water is left in the tank. So to save us all kinds of effort, we came up with some neat electromechanical devices to do the hard work while we stay safely on the ground and warm in the winter without having to play with frozen sticks, unless hockey's your thing. So let's look at how the signals are organized. Process control, we can separate any automated process basically into two sides. There's the process side, what we're trying to do, and then there's the signal and control side, how we accomplish it. The process side is concerned with the process we are trying to control. It focuses on the desired values and the current real-world value of the process. The signal side is connected to the process with devices that physically work to make the process happen. So let's focus on the process side to begin with. The process side determines the amount of energy or material we're controlling. Basically, it's the process variable. So the process variable itself has natural limits. For example, if we're talking about temperature, the natural temperature for water is 0 degrees Celsius to 100 degrees Celsius for freezing to boiling. However, we may not need the entire natural limits. Some people like a hot bath and some like a cool bath, but nobody wants a freezing or a boiling bath. We come to our first key term, range. Range is the boundary of values between the minimum and maximum limits of a process variable. When controlling a process, a range of acceptable values is determined. The range has an upper limit, or an upper range value, and a lower limit, a lower range value. To determine the range, you simply take the upper range value and subtract the lower range value. Here we see a vertical receiver tank. We do not want the water to overflow over the top, so we arbitrarily set the upper range value at 20 inches. And to make sure it does not go completely empty, we set the lower range value to 2 inches. This means our range is 20 minus 2 for 18 inches. Now let's take a look at the signal side. The signal side governs the signals that controls the process. Since this side deals with the primary, control, and final elements, we must work with the signals involved between these components. Depending on the device or system chosen, there are a variety of signals used. The primary element could be a simple pressure limit switch that indicates whether the desired pressure is present or not. Alternatively, a float switch could track the rising or falling level of the tank. Whereas in the first instance, it's only on or off, the float signal may be of a type that changes as the tank fills. This signal would be proportional to the level of the fluid in the tank. Here is another key term to remember: standard instrument signal. By definition, a signal that is used in industry to control devices is a standard instrument signal. It can be 0 to 5 volts DC, 1 to 5 volts DC, 0 to 10 volts DC, 1 to 10 volts DC, 0 to 20 milliamps DC, or 4 to 20 milliamps DC. And in some cases where you can't use electricity because of explosions, etc., where a possible spark is dangerous, you may have to go to a pneumatic signal of 3 to 15 pounds per square inch of air pressure. This brings us to our next key term, span. Span is the difference between the highest and lowest value of a signal. It's simply found by taking the signal maximum and subtracting the signal minimum, just like we did with range and the lower and upper range values. For example, if our signal is between 20 and 4 milliamps, or 4 to 20, and we turn it around, then you would have a span of 16 milliamps. Other signals are also used, but all follow the same premise, that the maximum signal is always provided at 100% of the process variable, and the minimum signal provided is always at 0% of the process variable. Here's another key term and a key concept, zero. Normally we think of zero as being nothing. Here, zero takes on a slightly different meaning. First of all, when it comes to the signal, zero represents the minimal signal sent. So in the case of a 4 to 20 milliamp system, 4 milliamps is the equivalent of that system's zero signal. It's the lowest or minimum signal of an output from an instrument. It's not necessarily the absence of any signal. Zero is used to adjust an output to its lowest value, or interpret the lowest input signal value possible in a process. It does not mean zero as a signal level, but rather it's interpreted as the rank or position. For example, if we're looking at 0% process variable, we want the lowest possible signal to be sent, and if it's 4 to 20 milliamps, 4 milliamps represents zero, minimal signal, 0% process variable. Just to clarify that we're still talking about zero as a signal, from the trainer station that we'll be working with, we have a transmitter, and that transmitter has an adjustment such that wherever the zero or lowest part of our process variable is, we're going to set our lowest signal or our zero signal to be sent out. On this particular transmitter, you have a choice between a 0 to 5 volt signal or a 4 to 20 milliamp signal. We will be using the 0 to 5. This brings us to the next key term, offset. The offset is the difference between the physical zero and the signal zero or process zero. It's the mathematical correction factor used when determining a true output or input value. It does not apply to systems whose lowest signal value is zero. For example, if you have a 4 to 20 milliamp signal, there is a 4 milliamp offset between being off and a true zero and our lowest signal, 4 milliamps. For the course we're going to be doing, we'll be using a 0 to 5 volt signal. Therefore, in any formula that requests an offset, we simply put 0. We've covered a lot of grounds and we've bombarded you with some new terms. So let's step back, take a quick review. There are two sides to any process. There's the process side, which deals with the abstract values and limits, the actual process itself we're trying to control. And a process side has ranges. To keep it straight, remember that process has an R in it and range starts with R. The signal side deals with signals and elements that do the work necessary for the process. The signal side has spans. Just remember that both span and signals start with S. For simplicity, this diagram shows us the process side of a transducer and the resulting signal side of a transducer. Idyllically, the span of the signal sent out will be a proportional image of the range of the process variable. Using some common sense, we can get a pretty good idea of how the signal will change as the process variable changes. Let's say our tank has 16 feet of possible water depth, but we're not going to count the bottom 2 because we always want to have at least 2 feet of water in the bottom of our tank. That would give us a process variable range of 14 feet of water. Now our signal goes from 0 to 5 volts. We have a span of 5. So it seems to make sense that every time the water would go up, say a foot, we should be able to figure out roughly how much the voltage should increase. So if we take the 5 volts and divide it by 14 feet, which is kind of weird, we don't do that in Ohm's law, but if we take 5 and divide it by 14, we end up with 0.357, and that would be volts, because we're looking at the signal. So for every foot the water goes up, the signal should increase by 3.75 volts. And every time it goes down a foot, it should go down about 3.75. Now, there is a formula which we're going to take that gets into a little bit more detail to make sure we capture everything, but we've pretty much done it here. This is the simplified version, and we're going to go through it in detail in our next video. Until then, thanks for watching.